So first of all, let's talk about the problem that they came to when they started dealing with static situations like Precal, where I said, hey, give me the slope of this line. And you're like, oh, y2 minus y1 over x2 minus x1, slope, we've got it. And so that's easy when you have a line. But if I said, what's the slope of this parabola? You would say, well, where, right? It changes. The slope of the parabola changes depending on where you are on the parabola. And so then all of a sudden we have a problem. I can't just hand you a slope with some formula because it depends on where on that line I am as to what the slope is. And so what they used is they used limit theory. And they said, well, let's take this secant line here. Pick these 2 points. Find that slope. That's the slope over here, right? Well, that's great, except you have this little gap and it's not technically the exact slope. And that's a pretty broad range of that parabola. So then they said, well, let's put these closer together. Okay, that's the slope. Oh, let's put them right on top of each other. That's the slope. And so what they're actually doing is they're saying the distance between the points is getting infinitely closer. So if I were to subtract those 2 points, I'm getting closer and closer and closer to 0. Because I want those points to be as close to possible and still be able to find the slope. And so that's where they come up with this formula here. We're trying to say, now this should look vaguely familiar, f of x plus h minus f of x over this h here. This is actually based off of your slope formula, all right? H is the distance between the 2 x's, okay? So h is the difference between the 2 x's, and I've plugged in one x and plugged in another x. That's the difference between the 2 y's. So I have y2 minus y1 over the difference between my x's, which would be x2 minus x1. This is your slope formula from way back in like geometry, all right? But what we're doing is we're trying to use the limit of what happens as those move to be the same point. So we actually get the tangent line. The slope of the tangent line is what this formula gives you. It is the slope of the tangent line at a specific point. So then I can say, well, the slope of the line here is this, and the slope of the line here is this, and the slope of the line here is this. And so all of a sudden, anywhere on that parabola, I can figure out what the slope of the tangent line is, okay? Using limit theory. Limit theory is the long way to do this, but I'm going to show it to you here, all right? Instantaneous rate of change. Okay, this is something else. When we look at rate of change, that's just a way of saying slope. We just used it when we were doing like different units. Like if you're going 50 miles per hour, right? Hours and miles are 2 different units. So we use rate of change, but we still use the slope formula. And so when I say instantaneous rate of change, I would say, if you drive from here to Columbia, your average rate of change, well, that would be the regular old slope formula. y2 minus y1. I would say my miles divided by my hours overall. It's not like you drove 60 miles an hour leaving the parking lot, but your average from here to Columbia could be 60 miles an hour, right? But definitely not on Ashley Phosphate, right? So I'm talking about average. This all of a sudden is going to give my instant. All right, when you are 45 minutes down the road, what was your exact speed? This is what you can calculate with calculus. You can't do that with pre-calculus. And so this formula with limit theory all of a sudden helps us do an instantaneous thing. Instead of giving the average slope over this line here, I want the instantaneous slope at that specific point on this curve. The instantaneous slope, instantaneous rate of change is what it's called. And so you actually do this by plugging in this formula, all right? Now, h is my x value here. My x value being 1. So my x value here is 1. I want to find my instantaneous rate of change. And so I'm going to do that using this formula. F of x plus 1 minus f of x all over my h being 1, right? Okay, and so I am going to, and they actually didn't plug it in yet, so we'll just do it the way they did it. So f of x plus h minus f of x over h, all right? They didn't plug it in, so we will do it the way they did it. All right, so I'm going to figure this out. Now what I'm going to do is I'm going to take the f of x that they gave me. Well, f of x is just another way to say y, correct? So f of x equals x squared. So think about when we plug stuff in. I'm going to plug x plus h into that, right? So I'm going to say f of x plus h is just x plus h squared. Minus f of x, we're just going to say, is x squared. That's what they told me, all over h. Okay? Keep in mind, this is a long way to do it. We're going to do it the short way. Don't stress. All right, so I'm going to FOIL this guy, which gives me x squared plus 2xh plus h squared minus x squared all over h, right? I just FOILed it. We can cancel some things. What can I cancel? The x squared 0 out, right? Is there anything else I can take out of this bad boy? An h out of everything, right? So I'm doing the limit as h approaches 0 of 2x plus h. What can I do with that 0? Plug it in. Originally, there was a problem, right? With my h. It's as h approaches 0, not x, okay? So originally, there was a problem. Now I've eliminated my problem, right? So I'm just plugging it in. So my limit here is going to be 2x, all right? 2x. They want it at a specific point. Now, what I have just done is I have found I can use the 2x and pick any point on that line, and that's going to be the rate of change at that point. They want it specifically at 1, so I'm going to plug in a 1 here. 2 times 1. So my slope at the point 1, 1 is going to be 2. That's my slope. That's my slope of this line right here, 2. All right? I can actually see that on the graph. Up 2 over 1. I can see that on the graph. That's the slope at that point. Okay? But that's my slope. And 2x represents any point on the line. Any point on the line, that is going to be my slope. If I want to say what's the slope at 0, the slope at 0 would be 0, 2 times 0. What's the slope at negative 2? The slope at negative 2 would be negative 4.
So if it was like 1, 3...
I would use just the x value, plug in the x value. All right. So, and you can see that here. So if I were to do a tangent line here at 4, you can see that it's going to be probably a negative 4 slope. Okay. Or a negative 2. It's going to be a negative 4 slope. See, here's my negative 2. There's my tangent line right there. If I go down and over, you can see even when I sketch it, it's going to be negative 4. All right. If I were to do a tangent line here at 0, well, that's a horizontal line. Guess what my slope is of a horizontal line? 0, okay? And so this formula gives you 2 ways to do it. It gives you an instantaneous at a specific point, or you can find the function where you can plug in any point and find it. So this is where the pattern comes into play. I'm going to look at this next one. This is at any point. I actually don't want to do that one. I want to do these. Okay? When they want it at any point, you literally have to plug the entire thing into this. FOIL it, cancel out everything, and then plug in your 0. FOIL it, cancel out everything, plug in your 0, which is all fine and dandy until you have to FOIL this bad boy. You know what I mean? And then all of a sudden you have to plug in the x plus h here minus the x plus h. We really have to plug in x plus h for the whole thing, right? Minus the whole function all over h. And then you have to do that guy and simplify it. All right? So it's a booger to find, okay? Especially when it's big like this. But there's a pattern, all right? So I'm going to give you the function for this guy. The function for this one, so we start out with x squared minus 4x and plus 2. I happen to know what this is going to be if I do this whole thing out. It's going to be 2x minus 4. I know that's what it's going to be. Let's look at the next one, x cubed. This guy's going to be 3x squared. There's a pattern. Let's do another one. X to the 5th is going to be 5x to the 4th. If I did 3x squared minus 2x, it would be 6x minus 2. Any pattern there?
Multiply the exponent by the coefficient and then subtract it by the coefficient.
There we go. So I multiply this guy over and I subtract 1 from him to get my new exponent. Okay? That is the pattern. And so if you were to do this for any function, that's the pattern you're going to see. All right? And it will give you the slope of the tangent line of that function. And it will give you instantaneous rate of change for that function.
So how did you do it for the...
So if I were to just take the ones they gave me here. So just take this first one. This is the new function. I can use that function to find any point. So if I wanted to find what's the slope at 0, 2 times 0 minus 4, negative 4. What's the slope of 1? 2 times 1 minus 4. What's the slope at the x value of 7? 2 times 7 minus 4. This gives me the function to find the slope at that point, anywhere on the function. In this case, a parabola. Okay? It doesn't matter what type of function. You can do it for any type of function. Okay? All right, so the term derivative, that's what you're going to hear with calculus, derivative. Derivative represents a new function. So you're handed a function which gives you a parabola, or it gives you a line, or it gives you a curved based on a cubic function, all right? And then derivative, this new function that you get from it can tell you the slope of the tangent line. It's a new function. It can tell you rates of change, all right? In physics world, it can tell you velocity. Okay, so position to velocity is actually a derivative. So if you've done velocity in physics, that's actually a derivative from calculus. And so this derivative, or this new function that you're finding, can tell you all sorts of information about the function you just had. Okay, and so what we just did is we did the long way of finding this derivative using slope of the tangent line. And now we're going to start looking at the shortcuts. This is actually the formula to find derivative. You'll notice that it looks exactly like the instantaneous rate of change formula because they are the same thing. The slope of the tangent line, instantaneous rate of change are actually the problems that were presented for them to be able to find out, oh, this is a derivative, and it gives us a lot of information. All right, so we're going to use our shortcuts based on a pattern. The first shortcut we're going to use is the power rule. The power rule says that if you take your original function and you want to find your derivative, you can take the exponent and multiply it to the front, and then subtract 1 from your exponent, and that is your new function called the derivative, okay? So let's look at the example. These are simple, all right? So I am going to take this function. They want the derivative. It is notated. When you take a derivative, you have this little dash above it. That indicates it's the derivative. So you take whatever function they gave you, you put that little dash, and then the power rule says I'm going to take this 9 and I'm going to multiply it in front. 9x, and I'm going to subtract 1 from the exponent to the 8th. 9x to the 8th. Simple. This guy. All right, first thing I'm going to do is I'm going to rewrite him. Fractional exponents look like this. Index is the numerator. Exponent is the numerator. Index is the denominator. So I can rewrite a radical like this, okay? Then I'm just going to use my power rule. The derivative of g of x is going to be, I'm going to take that 7/5, multiply it in front, x to the, subtract 5/5, 2/5. You can rewrite it if you want to, 7/5, 5th root of x squared, but these are the same thing.
Wait, why is it 2/5?
I subtracted 1, which is 5/5. Common denominator. All right, look at the next one. So ones like this you will rewrite. How do I rewrite this guy? X to the what? Negative 8th, right? Denominators are negative exponents. Pull that negative in front, negative 8. X to the, we are subtracting 1, negative 9. So I would rewrite that. I would rewrite that like this, negative 8 over x to the 9th. Okay? So go ahead and try those. All right, so this guy's easy. It's just going to be 4x cubed, right? This one you rewrite. So we have x to the 3 halves. All right, so I'm going to pull the 3 halves in front and subtract 1, which is 2 halves. X to the 1 half. All right, so that's what that looks like. This guy, you would rewrite with a negative 5. Pull it in front and subtract 1. All right, so it would look like this. Negative 5 over x to the 6th. They're simple. a derivative of a constant is just 0. It makes sense, right? Because if I have just, like say my f of x equals 5. Well, that's the same thing as 5x to the 0, right? So, I mean, if you multiply it by 0, it doesn't matter what you do to the exponent. It's going to be 0. So any constant, the derivative of any constant is just 0. It zeroes out, okay? If you have a number in front of it and you have to multiply by that exponent, just multiply it by the number, okay? And then if you're adding multiple pieces, you can take the derivative of each individual piece. So let's look at some of these. All right. I'm going to take the 3 and I'm going to multiply it in front. So I have 3 times 5, which is, and then my new exponent is going to be 2. And what happens to my 4?
0.
It zeroes out. So that is my derivative. All right. Okay. What about this guy? What do you want to do here? It's being multiplied. So let's go ahead and distribute that through. Okay. So x to the 5th times 2x cubed is 2x to the 8th plus 4x to the 5th. Okay. So now I'm going to multiply this through 16. My new exponent is 7 plus the second piece of it. Multiply that through 20. My new exponent is 4. Good. Look at this hideous thing here. That's really not bad. All right, so I'm going to rewrite this a little bit. So I'm going to say 5x cubed over x minus 12x over x plus 6x to the 5 halves over x. Okay, that's all that means, right? Do you see what I did there? And then I'm just going to take out an x about all of them. So take one of those, take one of those, and take one of those. So I have 5x squared minus 12 plus 6x to the 3 halves. And now I just do them individually. This multiply through 10x to the 1. Constant zeroes out. Multiply this through. Plus 3 halves times 2 is what? 3 halves times 6 is 9. X to the 1 half. Or you can say 10x plus 9 square root of x.
I don't know why that like hurt.
This is worded. The distance a particle moves along a path is defined by this function, where t is given in seconds and the distance of the particle is given in centimeters. Find the expression for the instantaneous velocity. When you see those words instantaneous and they've given you a function before it, the s of t is your position function, all right? S of t is your position function, meaning where it is located. The derivative of the position function is velocity. always. So if they say instantaneous velocity at a specific point, then what they are saying is they want you to take the derivative of the position function. That's literally all they're saying. If they give you the position function and they ask for velocity, they're asking for the first derivative, period. So you literally just have to look at this and say, oh, okay, well, we're going to take the derivative then of this guy. So derivative of the, let's write it in smaller than that. That would be ugly. All right. 18t minus 3t cubed minus 1. All right. 18t. What's my exponent on this guy?
It's just 1.
So 1 times 18.
18.
And then subtract 1
It's 0.
to the 0. What's anything to the 0 power?
0.
It's 1. So anytime you have just 3x or 5x or 8t, your derivative is just going to be the coefficient, all right, because it's to the first power. So 18 minus, and then 3 times 3 gives us 9. Drop one of your exponents, t. This is my velocity function here. 18 minus 9t squared. Velocity from position. So what would this guy be? What would my velocity be for this soccer ball that they've kicked? If that is my position of the height, my height position, what would my velocity be? Well, what's the derivative of 55t?
55
Just 55 minus 2 times 16, 32 t. That would be the velocity of the soccer ball. And then if they said at 3 seconds, guess what you would do? Plug in a 3. So after 3 seconds in the air, the velocity of that soccer ball is negative. Obviously, it came down before 3 seconds.
Wait, what'd you plug in for?
If they told us a seconds and they wanted instantaneous velocity at like 1.5 seconds, you'd plug in 1.5 into the time.
Wow. It's a negative.
All right, so in graphs, you have these turns, all right? Don't forget what we originally had the problem with, the slope of the tangent line, okay? So the slope of the tangent line at these curves, what is the slope of these lines? That's a horizontal line. What's your slope there?
0.
Mm-hmm. And so one way you can tell if it's turning is if it has a slope of 0 at your tangent line. So what you can do is you can take your function, they give you some function, whatever it is. Take the first derivative and say, where is that 0? Set it equals 0 and find those, and you will find your turns in your function. Because everywhere it turns, you're going to have a 0 as a slope. Think about it on a roller coaster. When you're at the top of the hill, you're horizontal to the ground. When you're at the bottom of the valley, you're horizontal to the ground. Going up, going down, your slope changes. And so first derivative can also tell you where your max and mins are, where your peaks and valleys are of a function. All right?